I'm Tara Murphy. I'm an astrophysicist here at the University of Sydney, and I research in radio astronomy. So I look at extreme events that occur in the distant universe, try to work out what's going on, and use them as a laboratory for studying physics. My research is in radio transients, which are astronomical objects that change rapidly on human timescales. So this means that they're extreme events that are happening in the universe. So for example, when a massive star dies, its core collapses and there's a huge explosion that goes out into the interstellar medium. We detect the radio emission from that explosion, and we can use that to work out the physics that's going on. The reason that's important is because the conditions in these explosions are unlike anything we can create on Earth. There's much higher densities, and the particles are moving at relativistic speeds. So this allows us to study physics in a way that we can't do elsewhere. Data is absolutely critical to everything I do in astronomy. Whether it's observational data or, with some other astronomers, simulated data, data is the way that we see the universe. So I use data in astronomy ranges from everything from images to spectrum when you're looking at different frequencies, to time series when you're looking at how an object evolves over time. We can look at data cubes, which have all of those things together. And one of the things that you might have heard about astronomy is the size of our data sets is huge. So the new planned telescope, the Square Kilometre Array, we use the expression a petabyte a night. That's how much raw data we'll be taking every night that we observe with that telescope. So there's not one bit of astronomy that I do where data isn't critical. So one of the data sets I use, or one of the ways in which I use data to look for these rare transients, is that in a radio image, we have lots of astronomical objects, which we call sources. And most of those sources are supermassive black holes in distant galaxies. Most of them don't change at all on human timescales. So if we took the image of that patch of the sky, and then we took the image of the same patch of the sky, but a year later, it would be exactly the same. Most of those sources evolve on millions of years of timescale. But occasionally, something changes. And there was an example of that last year with this famous gravitational wave event, the two neutron stars that emerged. A new object appeared in the sky, something that wasn't there the day before. And that new object is the signal from the explosion caused by those neutron stars merging. So what I do in my research is look for those rare signals in an otherwise unchanging sky. Because data is absolutely central in astronomy, I think the most important thing is having an intuition for whether your data is correct or not, because every bit of science that we do is based on understanding that data. And so the data analysis that I do ranges from everything from how to store and transport huge, petabyte data sets of data, right through to analyzing catalogs in a database, and so doing queries and analysis, and then further through to machine learning to classify different objects. So really the most important thing about all of that whole stack of data analysis, is that you have a good intuition for your data and you understand its limitations so that you can do analysis on it. I think data science has always been part of astronomy, well before it was ever called data science. Data science is like the rest of the world catching up with where astronomy has been for a long time. When I think of data science, I think of doing data-driven science, which means that you start with some hypotheses about what you might expect to get from this data, but you are then guided by your understanding of the data, and a lot of it is iterative. You follow directions depending on what comes out of the data as you do your initial analysis. So I think in the future, this will be even more important in astronomy. Long gone are the days where astronomers could just look at individual objects by hand. Almost every astronomer is now doing computational analysis all the time. And so, I think it's impossible to underestimate the importance of data science for astronomy. It's completely central to it. Looking back at my own education and how it's been useful for my career as a scientist, I think nothing is more important than your ability to understand and develop an intuition for data. And I think that what that means for a modern scientist is you need to have really good statistics skills, you need to have really good programming skills, and you need to be able to think in a computational and numerical way about solving your problems. So there's what you learn analytically about how physics works, but then there's how you actually test those things using the data, and in that is a lot of statistics and programming. So you need to be able to do that yourself with data, otherwise you can't understand it. The biggest danger that I see with students coming through and starting their own research projects for the first time is treating data analysis like a black box and not really understanding the process that's going on. If you've done your data analysis like a black box, you don't know whether you can rely on those results, and that's one of the most important things about science.